In 2009, astronomers were watching a red supergiant in a galaxy about 25 million light-years away. It was enormous, roughly 25 times the mass of our Sun, and it had suddenly begun to brighten. That usually means one thing: a supernova is coming. So astronomers waited for the explosion. But it never came. The star grew faint instead, then fainter, and when Hubble looked again, the star was simply gone. No blinding flash, no expanding wreckage, no clear corpse left behind, just an empty patch of sky where a star had been. The obvious explanation sounds almost impossible. The star may have collapsed directly into a black hole, and almost no one noticed. But that is not the strangest part. Years later, something is still glowing in the darkness where the star disappeared. So did astronomers witness the quiet birth of a black hole? Or is the star still there, buried behind its own dust? Tonight, we are following the evidence behind the vanishing stars. And the closer we look, the less simple the answer becomes. Before we go any further, we need to be careful with one word: vanished. Astronomers do not look at one old photograph, notice a missing dot, and declare that a star has disappeared. The sky is messy. A source can fade below a telescope's detection limit. It can move. It can be hidden by dust. An asteroid can cross an image at exactly the wrong moment. And old photographic plates can contain scratches, chemical marks, or defects that look surprisingly star-like. So a real vanishing star has to survive a long list of boring explanations. It should appear in several observations before the event. It should remain missing in deeper images afterward. And ideally, astronomers should search the same location in infrared, radio, and X-rays. Because darkness and visible light does not necessarily mean that the object is gone. It may only mean that we are looking in the wrong kind of light. That distinction matters. The mystery is not whether dots sometimes disappear from photographs. They do. The real question is whether an actual massive star can die without producing the brilliant explosion we have been taught to expect. A massive star spends most of its life doing one thing: holding itself up. Gravity is constantly trying to crush it inward. Fusion in the core pushes back. For millions of years, that balance works. Hydrogen becomes helium. Helium becomes carbon and oxygen. In the largest stars, the process continues through heavier elements until the core fills with iron. And iron changes everything. The star can no longer gain useful energy by fusing it. The pressure supporting the core begins to fail. Then, in less than a second, the core collapses. Matter falls inward at a significant fraction of the speed of light. The inner core is compressed to extraordinary density, and a shock wave begins moving outward. This is the beginning of a supernova, but it is not yet an explosion. The shock has to escape, and sometimes it cannot. The term failed supernova is slightly misleading. The star does not fail to die. The explosion fails to escape. Think of trying to set off an explosion at the bottom of a waterfall. Even if the blast begins, material keeps pouring down on top of it. Inside a collapsing star, the situation is far more extreme. Gas continues falling toward the core. The newborn neutron star becomes heavier. If it crosses the limit that matter can support, it collapses again. This time, into a black hole. Most of the star may then follow it inward. From the outside, the result could look almost disappointingly quiet. Not completely silent, though. The collapse releases an enormous burst of neutrinos. As those particles carry energy away, the central object loses a small amount of gravitational mass. In a swollen red supergiant, that tiny change may be enough to send a pressure wave through the outer envelope. Some of the outer gas can drift into space. Instead of a normal supernova, we might see a faint, red, and slow-moving outburst. Something easy to overlook in another galaxy. Then the glow fades, and the star does not come back. The best-known candidate is called N6946, BH1. The name is forgettable. What happened is not. Before 2009, it appeared as a luminous red supergiant in the galaxy NGC 6946. It shone with roughly 300,000 times the luminosity of the Sun. Then it brightened, not like a full supernova, more like a warning flare. For several months, the star reached more than 1,000,000 times the sun's luminosity. Then its visible light collapsed. By the time Hubble examined the site, the red supergiant was gone. At first, the story looked almost perfect. A massive star had produced a weak outburst, disappeared in visible light, and left behind only a faint infrared glow. No clear X-ray source appeared. The remnant continued to fade. This was roughly what a failed supernova was expected to look like. Part of the outer envelope escapes. The core collapses, and most of the remaining star falls into a newly formed black hole. There is another reason this object matters. Astronomers have noticed that the most massive red supergiants seem strangely absent from many images taken before ordinary supernova explosions. We know those stars exist, but when astronomers search old photographs for the stars that later exploded, the most massive examples rarely appear. Some researchers call this the red supergiant problem. One possible answer is that the largest red supergiants do not always produce bright supernovae. Some may collapse quietly. For years, in 6946, BH1 looked like the missing example, but science rarely gives us a mystery that clean. Then the James Webb Space Telescope examined the location, and it found something still glowing there. A dusty infrared source remained at the position of the missing star. That does not automatically mean the original star survived. A newborn black hole can be surrounded by material that failed to escape. Dust in the expelled envelope can absorb visible light and release that energy again in the infrared. Nearby stars can also blend together in lower resolution images, making the original source look brighter than it really was. JWST separated several neighboring stars from the remnant, and the source associated with N6946, BH1, was still far dimmer than the original supergiant, roughly an order of magnitude dimmer. That matters. Known stellar mergers often remain as bright as, or even brighter than, the stars that produced them. This object did the opposite. It lost most of its luminosity and never recovered. So the failed supernova explanation remains strong, but it is not proven. The remaining infrared light still has to come from somewhere. It may be dust and fallback materials surrounding a black hole, or it may be a surviving star hidden inside a structure more complicated than the simple dust clouds used in early models. The most honest answer is this: the original star is still missing, but the darkness is not empty. Then astronomers found another candidate in the Andromeda galaxy. It is known as M31-2014 DS1. This object brightened modestly in the infrared. Later, its visible light fell dramatically. Its total luminosity also dropped below the level of the original star. Again, the pattern suggested a weak mass ejection followed by collapse into a black hole. And again, JWST complicated the picture. It found a very red infrared source at the same position, surrounded by gas and dust. X-ray observations found no obvious bright source. Now, two teams can examine nearly the same evidence and tell different stories. One interpretation says the star collapsed into a black hole. A small amount of material may still be falling inward, producing a faint infrared remnant. Another interpretation says a star, or the product of a stellar merger, may have survived. An uneven cloud of dust could be hiding much of its light from our direction while allowing the energy to escape elsewhere. This is not a failure of science. It is science happening before the answer is known. When the evidence is incomplete, disagreement is exactly what should happen. M31-2014 DS1 is not proof of a failed supernova. It is a test case, and the competing explanations make different predictions about what astronomers should see as the dust expands and the object continues to evolve. There is another way to search for disappearing stars. Instead of waiting for one nearby star to vanish, researchers can compare old maps of the sky with modern ones. That is the idea behind VASCO, vanishing and appearing sources during a century of observations. Researchers used photographic plates from the first Palomar Observatory sky survey, mostly taken during the 1950s. They compared those images with modern catalogs, such as Pan-STARRS. The first automated cross-match produced a dramatic number. About 150,000 sources appeared on the old plates, but had no obvious counterpart in modern optical catalogs. That sounds like an army of missing stars. It was not. The team visually examined a smaller subset of roughly 24,000 of those candidates. Once they searched other archives, almost all of them were matched with known objects. Many were visible in infrared. Others were asteroids, variable stars, fast-moving stars, or defects in the photographic material. Around 101 epic transients remained flagged as genuinely interesting. But even that does not mean 100 stars disappeared. Most appeared on only one old exposure. That makes them interesting. It does not make them secure. A genuine failed supernova candidate should ideally appear in multiple images before disappearing permanently. In this search, no object met the cleanest version of that standard. That may sound disappointing, but it tells us something important. True stellar disappearances are extremely rare, and proving one requires far more than finding a mysterious dot on an old photograph. Whenever stars disappear, one idea arrives almost immediately: alien megastructures. In principle, an advanced civilization could build enough structures around a star to change the light reaching us. That makes unusual dimming events relevant to searches for technological signatures. But there is currently no confirmed vanishing star that requires an alien explanation. Before reaching for technology, astronomers have to eliminate dust, variable stars, asteroids, stellar mergers, weak eruptions, failed supernovae, catalog errors and defects in old photographic material. Aliens are not scientifically forbidden. They are simply very far down the list. And in these cases, the natural explanation is already extraordinary enough. We may be watching stars become black holes without producing normal explosions. So how could we prove that a star truly collapsed into a black hole? First, we need clear images of the star before the event. Then we need repeated confirmation that it remains missing. After that, we need every wavelength we can get. Infrared observations can reveal hidden dust and surviving stars. X-rays can search for hot material falling toward a compact object. Radio observations can detect expelled gas colliding with the surrounding environment. A neutrino burst would be especially important. It could tell us that the core collapsed even if the star produced almost no visible light. And if that neutrino signal ended suddenly, it might suggest that the newborn neutron star itself collapsed behind an event horizon. Gravitational waves could provide another piece of the event. No single telescope may solve this mystery. The first undeniable failed supernova will probably be reconstructed from several instruments watching the same star die in different ways. Not one photograph, not one missing point. A complete physical record of a star collapsing and failing to return. Somewhere in a nearby galaxy, a massive star may be approaching this moment right now. Deep inside it, the iron core is growing. Soon, gravity will win. The core will collapse. A shock will form. And for a few seconds, the star's future will depend on a struggle no telescope can see directly. If the shock escapes, the galaxy will gain a new point of light bright enough to rival billions of stars. We will call it a supernova. But if the shock dies, the star may do something much quieter. Its outer layers may swell and drift away. Its light may turn red. Then the core, and perhaps most of the star, will fall inward. The final image will not show an explosion. It will show what is missing. For now, in 6946, BH1 remains one of the strongest candidates we have. M31-2014, DS1 remains an open argument. And century-long searches remind us how easy it is to mistake an artifact for a cosmic disappearance. But they also leave us with a possibility that is difficult to ignore. Some black holes may not announce their birth. They may enter the universe as an absence, a star that was there and then never returned. If you want to keep exploring the most hostile and unexplained corners of the universe, subscribe to Hostile Orbit and face the void.